Hello and welcome to video 24. This is a slide that I rode in college. We used to drive an hour to ride down a toboggan that was on an ice hill, really. The local fire department there would actually cut blocks of ice from the lake, put them up the hill, and then people in 6 or 9 person toboggans can slide down. And you want going very fast by the time you get to the pond, and then you go out onto the pond. It's really something that's cool. In fact, I've linked a YouTube video here to somebody that's done it a little more recently than I have. And I estimated the run of the hill to be 175 meters down the hill, 15-degree incline, and we're going to assume that the coefficient of friction is 0.1. And what I'd like to do is figure out how fast you go at the bottom of the hill. Then once we've figured that out, we're going to figure out, it's a lot of figuring out, isn't it? But we're going to determine how far you go out onto the lake, because the friction on the lake we're going to assume is the same coefficient of friction as on the ice slide, and we'll calculate how far you go on there. Then once we've done those work energy calculations, C and D aren't really energy calculations, they're kinematics, but it's still kind of interesting to calculate how much time it takes to get to the bottom of the hill and how much time it takes to stop once you're on there, and then correlate this with the linked video and see how close we come to real life. So what we want to do is sketch a picture of the situation, and what happens is it's really a two-part problem. In the beginning, you're going to go down the hill, which we're assuming is one straight triangle. It's not exactly what the hill's really like. So we're going to assume a nice hill that we're going to go down in our toboggan. The angle theta is going to be 15 degrees. And as you go down this hill, in the beginning, you're going to have some potential energy due to this height. And you're going to go down some length of a run, d. Now this height, it's worth pointing out right off the bat, is equal to d sine of theta. You can see that because that's the opposite side. This is the hypotenuse. And let's look at the total mechanical energy at the top versus at the bottom, and here's a situation where there is going to be non-conservative work done by friction. So we have the total mechanical energy in the beginning, or at the top of the hill, plus any work non-conservative, which there definitely is due to the friction, equals the total mechanical energy at the bottom. Now at the top, it's all going to be potential energy mg h, but we just said h is d sine of theta, so I'm just going to do that in this first step and say mg d sine of theta is the gravitational potential energy. There's no spring potential or anything like that. So now as you go down the hill, you're going to have work non-conservative. That work non-conservative is going to be done by friction. Well, the friction going down the hill here is going to be equal to mu times the normal force. And the normal force, because we're on an incline, is going to be, instead of just equal to the weight force, it's only going to be part of that weight force. It's equal to the part that's perpendicular to the incline, which, if you recall, is mg cosine theta. If you need a refresher on that, you can go to video 8. So I'm going to erase this F. And the friction force is going to be mg cosine theta times mu. That's the force. And then, remember, work is force times displacement. It's going to be the distance d down the hill. Now when it gets to the bottom of the hill, we're going to assume that all of the energy that's still in the toboggan and the sledders is going to be in kinetic energy. So that's going to be 1/2 times m times the velocity squared. This is the fun part, the part we're interested in. Right here. That'll be fun. Now I did not give you the mass of the sled, and it really doesn't make much of a difference. When you start factoring in air resistance, it can make a difference, the weight to surface area ratio, but it's small enough of a difference that we're just going to ignore it completely. So the m's cancel out, and we're going to bring the 2 over here, or even before we do that, let's do a little algebra, a little factoring out here. There's a g and a d in both terms, so we're going to factor out the g and the d. So that leaves you with times sine of theta plus mu cosine theta. And I'm going to bring over this 2, which is like this. And since this is v squared, v is going to be the square root of this stuff. So I'll just draw a box around this. So this is an expression for the velocity at the bottom. Now let's go ahead and put in the numbers now, get it over with. Besides, who can wait when you're having this much fun? And the distance was 175 meters times the sine of the angle, which we decided was 15 degrees. Well, we didn't decide. The land was sort of made that way. Plus the mu is 0.1 times the cosine of 15 degrees. When you multiply all that out, you get a velocity that is 23.6 meters per second. Now, for those of you who don't think metric, this is about 50 miles an hour. So that's a pretty good run. That's definitely a lot of fun. Now, there's a second part when we get to the bottom of the hill. You're going to take some distance to stop. I'm going to call that distance x. And we're going to assume that all of your kinetic energy here is dissipated by the friction, taken away by the friction. So we're going to take that 1/2 mv squared you have at the bottom and set it equal to the friction force times the distance. Now, if this is v squared, we're just going to take the square root away. So it's going to be 1/2 m times 2gd times sine of theta plus mu cosine theta is going to be equal to mu. Now in this case there's no cosine because we're on the flat, so it's going to be the same magnitude as the weight force, mu mg d, or really I should say this is x, and we want to solve for this x. So we're going to divide this over. By the way, let me just cancel out these. The mass cancels out. When you solve for x, you get x equals, while we're at it, let's cancel out the g too. You get an x that's equal to d over mu times the sine of theta plus mu cosine theta. Again, let's go ahead and plug in the numbers. The d, the run down the hill, was 175 meters. The mu was 0.1. The angle was 15 degrees. When you plug all of that in, you should get an x of 283.9 meters. Now when you add on the 175 meters that you went down the hill, you get a distance of 458.9 meters, which is actually really close to the 1/4 mile or so that the toboggan is listed at. So we figured out the kinetic energy at the bottom. We figured out the velocity at the bottom. We've figured out the distance that it would take to stop. All these things are work energy things that you want to be able to do. Now, while we're at it, this is a lot of fun. Just because we're in an energy unit doesn't mean we can't talk kinematics. When you look at the forces on this person, or persons, really 9 of them, as they're going down the hill, during the downhill portion, there are really 2 forces in the direction of motion. On the one hand, you've got the mg sine of theta, or the weight component down the hill, speeding you up, and slowing you down, you've got the coefficient of friction, mu mg times the cosine of theta. And that, of course, is equal to mass times your acceleration. Mass cancels out, and you get an acceleration that is equal to some fraction of g. That fraction is sine of theta minus mu cosine theta times g. So when you put in the numbers, okay, sine of 15 degrees minus 0.1 times the cosine of 15 degrees times 9.8 meters per second squared, you get an acceleration that is positive 1.59 meters per second squared. You'd expect positive because you're going down the hill, and you would expect it to be less than 9.8 because you're not falling, but it is positive. Once you're in this region over here, your acceleration is going to be negative, and at that point the only force acting in the direction of motion is going to be the friction force, and that friction is going to be mu mg, again no cosine theta because at this point you're flat, that's going to equal ma. So at the bottom your acceleration is just mu times g. Really your acceleration is going to be negative because the friction force opposes your motion, so we'll say negative mu g, and when you put in negative 0.1 times 9.8 meters per second squared, the math's easy, you get negative 0.98 meters per second squared. So you get a negative acceleration because you are slowing down. So now that we have the acceleration, we can go ahead and figure out how much time did it take to stop, and we can corroborate that with what we saw in the video. So if we look at the acceleration by definition is change in velocity over time. Well, that change in velocity on the way down was going from 0 to the 23.6 meters per second over, well, the acceleration was negative. It was 1.59 meters per second squared. So really what I've done is I've said t equals delta v over a. And that gives us a time on the way down of 14.8 seconds. Go ahead, watch the video, see how close you think that comes. And over here, the time to stop, we get the same thing, change in velocity over a, and that's going to be, in this case, negative 23.6 meters per second over negative 0.98 meters per second squared, and that gives us a time there to stop of 24.1 seconds. And when we add those two things together, we get a time that is a little closer to 40 seconds. So you can go ahead and you can corroborate that with the video, see how well that goes. The last thing I want to do is bring up a spreadsheet I created, because that's what I like to do, and it really does let you analyze the situation. So here you can see we have a 175 meter run, 15 degree hill, coefficient of friction 0.1. That's giving a stopping distance of 458.9. I think the actual stopping distance winds up being a little less, closer to the 400 figure, because at some point you start running into snow and things like that. Well, what can we change? What can we play with now that we have this spreadsheet? Let's say that that ice gets kind of wet. What that's going to do is that's going to possibly increase the coefficient of friction, or maybe if there's a little bit of snow. Let's just say, for argument's sake, you doubled the coefficient of friction to 0.2. What do you think that's going to do to these numbers? What do you think that's going to do to your speed at the bottom? And what do you think it's going to do to your total distance? Well, if I double it to 0.2, my speed drops to 33 miles an hour versus 52, and the stopping distance drops considerably. So it cuts almost in half. So again, 0.1, 0.2, clearly that makes a huge difference. Something else we can't control, but I can vary, would be the height of the hill. At least I can vary in a spreadsheet. I can't make the hill any higher or slower, but let's just say the hill was twice as high. Let's say it was 350 meters high. You would travel almost a kilometer to stop, and when you get to the bottom, you would be somewhat faster, but not as much faster as you might think, mainly because the friction slows you down quite a bit, but it does take a lot further to go. I'm running out of time, but I hope you found this interesting and as enjoyable as I did, and if you ever get the chance, I strongly encourage you to go Eagles Mirror. It really is that much fun.